So we defined last time, and I will recall the definition, a differentiable function. Yes, I want to just ask you to look at these graphs and decide, do you think these functions are differentiable at the origin? So do you think there's a linear map that gives the best linear approximation to these functions at the origin? The origin is obviously the center point on all of these pictures. So perhaps it would help, and again I encourage you to play with Mathematica yourselves, to actually sit and look at it from different angles. So what, if you look in different directions at the origin, what do you notice in this function? Can you visibly see the directional derivatives in different directions? In this direction, what is it? As you go in this direction, in one of the axes, it's 0. If you turn it 90 degrees and go in that axis, it's also 0. But what is it if you go in this direction, along there? 1. Looks like it's going up at slope 1. And then down at slope -1 down there. So does that feel differentiable to you? No. What about this one? So what is this function on the axes? When you said x equals 0 or y equals 0, what's that function doing? It's identically 0. So this is another one that is 0, has 0 directional derivative in the direction of the axes. Does it seem to be having 0 directional derivative in all directions at the origin? No. So again, you would vote not differentiable. What about this one?
Yes.
What do you think is the best linear approximation to this at the origin?
Z equals 0.
If I stand too close to the screen, it doesn't look very clear. Looks like it's flat, right? Looks like you ought to have a flat tangent plane at the origin, and then it starts to bend up as you move away. Okay. And this one's similar to one of the ones I have above.
It's actually like a, yeah.
Or is it?
I think. No.
So this one appears to be flat if you go in the y direction. But if you go in the x direction, I should really stop turning this so that you can't tell which direction's which. In the x direction, it's going up at slope 1. In the y direction, it's going slope 0. But what about in other directions? Okay, so we're going to have to actually investigate a couple of these algebraically to decide what's going on. Now, I did not even show you the crazy one that wasn't continuous, because you know that can't possibly be differentiable. We're going to prove that today. Okay, so I want to actually try to come back to computing with some of these things and deciding. Oh, that helped. So let's review the definition. We call F mapping. So this was done for a general vector value function, but we're going to only do scalar functions. Neighborhood of A in Rn to Rm is differentiable at A if what? There is
linear map.
which we will usually call the derivative, with the property that if you take f at a point near A, so you displace your point by a vector h, and you look at how much it changed from A to A plus h, that can be well approximated by this linear map T. And well approximated, remember from what we did Friday, means that the error, this error between the actual change and the linear approximation, is what compared to the size of h? Small. So this limit, as h goes to 0, is the 0 vector. And then we said t is called, if such a t exists, t we'll write as df at A. Okay, so I had a bunch of comments on the board that we're going to slowly prove today and tomorrow. But let's actually do an example here. Oh yeah, so one of the things we'll prove was that, just to remind you, I said this on Friday, if f is differentiable at A, then first, the directional derivative can be computed in a direction V by applying the derivative matrix to the vector V. So in other words, the directional derivative in direction V becomes a linear function of V. Second, if you take the directional derivative in the direction of one of the standard basis vectors, that should be what? Or in the direction of the x-axis, the directional derivative should be partial. So if that's what you get when you apply this linear map to EI, that's going to tell you that the derivative map as a matrix, the standard matrix, is going to be the matrix of partials. I guess I should put J's here to be better. So the jth column of the derivative matrix is going to be the partial with respect to xj. That's what this is saying. The jth column is the partial of the function f with respect to xj. And so that's putting this together with how we make the standard matrix. Okay, so let's actually ask about some of the examples we looked at in those pictures. So one of the functions was x squared y, or xy, I don't remember, not that it really matters, xy squared, that's what I had there. Or x squared plus y squared when you're not at the origin, and then 0 when you're at the origin. So the question is, you do know from homework, because you actually did this problem almost verbatim, if not verbatim, this is continuous at 0. What was the argument for that?
You said x equal to y squared?
No. It is continuous.
Y squared over x squared.
Yeah, this fraction is bounded by 1, and you're multiplying it by x, which is going to 0. So that's why this was continuous at 0. Now, what about the partials at 0? Well, if you look on the x-axis, you set y equal to 0. And the function's identically 0, so the partial is 0. Similarly, the y partial. The question is, what's the directional derivative in the direction of the vector 1, 1? So don't just tell me this. Why?
We don't know that yet.
We don't know it's differentiable. In fact, if we suspect it isn't, we might be able to tell it isn't by seeing that this is not 0. So note, if f were differentiable, there's that subjunctive again, at 0, we would have that the standard matrix is the matrix of partials. That's what we said here, which we said were both 0. So every directional derivative at the origin would be 0. Well, let's see what it is for d in the direction 1, 1. So how, if I'm not allowed to use this formula, because I don't know f's differentiable yet, how am I supposed to compute the directional derivative?
By using that a plus.
Yeah, I'll go back to the definition. And don't fall in this trap. This is going to happen to you several times on homework, and I promise it will happen on the exam. So pay attention when you're doing these problems. So that if v is the vector 1, 1, the directional derivative in the direction of v at origin is the limit as t goes to 0, f of tv, so that's tt, minus f of 0 over t. And what is this limit? What is f of tt? So I'm putting in tt, t cubed over 2t cubed over 2t squared. Don't forget to divide by another t, minus 0. That's 0. Looks like it's a half. So it can't be differentiable. Because we just said if it were, the direction derivatives in all directions would have to be 0. In other words, if in the axis directions the graph of the function is flat, then if it were differentiable, it would have to be instantaneously flat in all directions of the origin. The best linear approximation would have to be a flat plane, which would mean as you go in other directions, you would still stay flat. This shows that it can't be differentiable. All right, well, what happens if we try the last picture I showed you, which had an x cubed instead of this? So this one's ruining the axis game. And then 0 at the origin, right? So now, what are the partials at the origin? Well, what about the y partial? So on the y-axis, x is always
0.
So what's the derivative?
0.
So the y partial is 0. What about the x partial? What's the function doing along the line where y is 0? It's just x. Note that f of x 0 is x cubed over x squared, which is x, when x isn't 0. And what about when x is 0?
0.
That's this rule. Does this function have a simpler way of being written? It's just x, right?
Yeah.
So what's the partial respect to x at the origin?
1.
Aha! Well, so we can try to play the same game we played up here. If f were differentiable at the origin, we'd have the derivative, the standard matrix is what? X partial is 1, and the y partial is 0. And now you could ask yourself, what's the directional derivative in an arbitrary direction? Is it going to work out okay or not? So let's go back to the definition again. So the directional derivative in the direction of a vector v I do f of tv, so we'll put in v1 and v2 as we did the other day, minus f of 0, which is 0, all over t. What do I get now? T cubed, t1 cubed, over
t squared times magnitude
v1 squared plus v2 squared, and then I have to divide it all by t, right?
So all your t's go away. Is that always 1, 0?
Is that what I would get when I multiplied this by the vector v? No. Does this equal question mark? One, 0. Didn't leave myself enough room. 1, 0 times vector v. No way. So, yet again, not differentiable. You could probably put in numbers and see, right? You put in the vector 1, 1 again, like we did earlier. This side would be 1, and this side would be 2.5. So they wouldn't agree. But you could also look at this formula and see it's not linear in V. And this side is linear in V. Okay? All right, well, enough of this negativity. Let's do some function that actually is differentiable. So seeing something isn't differentiable is a matter of using the contrapositive of this proposition or of showing some limit isn't 0. Right? As you know, proving something does have a limit is harder than proving it doesn't in general. So let's try to do one where it actually has. More interestingly, let's look at the function which is defined on all of R2 except where y is 0. And the function is going to assign to x, y, the quantity x over y. So if Dan remembers what we talked about at the end of Friday, he'll know what I'm doing here, and the rest of you don't remember. So the question is, do you think this is a differentiable function? This is the domain. Y isn't allowed to be 0. So do you think at any point A vector, where the second coordinate isn't 0, that this function has a derivative? Sure, why not?
I would imagine.
But how would you actually prove that a function is differentiable without having some theorems that we haven't learned yet, but we'll know soon?
You can take the matrix and partials.
I could take the matrix of partials. I could take the candidate
Yeah.
for the derivative and show that it satisfies that limit definition. And that's in fact what I have to do at this point. So what should be the derivative at a point vector A? So again, as usual, I'm going to make you upset by using vector A to be the point AB. What is the candidate for the derivative matrix? Well, as Taylor said, it's the matrix of partials. What's the partial with respect to x?
1 over y.
1 over y, so at this point,
1 over b.
1 over b. What's the partial with respect to y?
X over y squared.
Careful.
Minus
Negative.
x.
Negative x over y squared. At this point,
Minus a over b squared.
so to show that it really is differentiable, I have to put this linear map into that definition and prove that the limit is 0. Oh, joy. We must show, and I believe you will have one like this to do in homework as well, that the limit as the vector h goes to 0, f at a plus h, I'm writing it all with vectors at the moment, minus f at a, minus this matrix times the vector h, all over vector h, magnitude is 0. Lovely. All right, here we go. Brand new blackboard. So obviously, h needs to be given components just like a vector was. And to continue in my being obnoxious, I'm going to let vector h be.
HI.
Not hi. The alphabet just doesn't work well that way. So let's let h, the standard letters to use are h and k. Little h for the x variation and little k for the y variation. I's and j's just don't cut it here. I don't know. The alphabet, we should be in a different language. So what is f at a plus h minus f at a minus this matrix times vector hk? So let's actually write out what this is. What is a plus h?
A plus h over b plus k.
A plus h, b plus k. So f of that is x over y
Right.
minus
A over b.
a over b minus, now what did we get when we multiplied this matrix times this vector?
H over b plus
Minus.
Well, all right.
fine.
Right? That's what it is with the minus, and then you distribute. All right, well, let's see. What in the world? You guys used to know how to do algebra. How do we do this?
Multiply both sides by zero.
I don't want to multiply sides because I don't have an equation. I'm just computing this algebraically. But I want a least common denominator. Dan wants to square both sides, but that won't help. It might almost help on homework that you're doing this week, but not quite.
B
squared
cubed.
times b plus 6.
So I have a b squared.
B cubed plus k.
No, I don't need b
It's
cubed.
just b squared.
B squared times b plus k is the common denominator. So I have a plus h times
B squared.
b squared minus a times
B plus K. B times B plus K.
b times b plus k minus h times
B times B plus K.
times B plus.
Plus
plus ak times
B plus.
b plus k. And around this time, you guys are giving up.
Yeah.
The difference between me and you is
You don't
I won't give up. I'm just stubborn. So you guys have to learn to be more stubborn and not give up. All right, let's try to simplify that numerator.
b plus k.
So we could write everything out. Is
You
there
can
anything?
combine like terms.
I tell you not to write everything out in general, but is there,
Combine.
no, we don't need to add.
Combine like terms.
Combine like
We want to
terms.
combine like
Well,
terms.
we know there's a lot of b plus k terms.
There are a lot of b plus k terms, so maybe before we multiply, but they don't simplify
You
anyway.
can take it. Oh.
A plus h
Unfair.
b squared minus b plus k, well,
2 plus.
plus b plus k times ak minus
AB
hb
Minus
minus
A.
ab.
And then separate the numerator. Just curious.
Wouldn't it be better to multiply out the top part in group by powers of b?
Okay? So I'm going to have b squared times a plus h. Now how many b squareds do I have on this thing? Well, anything where I have a b here and a b here will give me a b squared. So I'm going to have minus a minus h. Oh, isn't that interesting? You see that? So that just took care of these two terms. Now what's left is a b times the first term back.
Minus
And then
k times
the
A.
k times the whole thing, right?
Yeah.
Negative back.
Negative, no.
Negative.
Back.
Oh, down there there's a negative back.
Yeah.
But here I have a cac, so I have an ak squared, and then I have a minus h, a bhk, and then I have a minus abk, which is another back.
Cancels the original.
So luckily for me, somebody had my back, and those cancel. And what happened to these?
That's zero.
That's 0.
This is not so scary anymore, guys. All that mess turned into
All that.
two simple, no, it's not so bad. Two simple terms. AK squared minus BHK over junk, which, now what, let's remind ourselves what we're trying to do. We're trying to look at this quantity
Over the magnitude.
over
Magnitude.
magnitude of the H vector.
Should you,
So I'm trying to look at all this stuff, which turned into this.
the magnitude of H is square root.
So I want to look at the limit as the H vector goes to 0 of this not so horrible stuff over magnitude of
A squared A squared.
h
This case
vector.
Everything has H and K terms, except for the B's.
Yeah, so,
So what do you notice about this? This stuff really isn't going to bother me, because when k and h are going to 0, this goes to b cubed. What's interesting about this is that I've got, so I'm going to put that out in front actually. And then I've got a times k squared over magnitude of vector h minus b times hk over magnitude of vector h. Does this look familiar compared to stuff we've done before? Maybe I shouldn't have even written it this way.
is it the third?
Oh, yes. Yeah, wait.
What do you know about k squared over magnitude of vector h and hk over magnitude of vector h?
Bounded. They're less than.
You know that each individual term like that, with a single power in the numerator, is bounded by 1. What happens when I have a quadratic?
Bounded by the.
Oh, it becomes k times.
Yes.
So they're both bounded by.
So what happens to the k squared over magnitude h? This is bounded by 1, and this
Bounded by K.
goes to
0.
0.
So what does this whole thing go to?
0.
Similarly, that one. It's the same limit game you played in homework 2 weeks ago. So both of these things, when I divide, these things both go to 0. This goes to 1 over b cubed. So the sum goes to 0.
That was only 1.5 whiteboards.
Right.
Blackboards.
Well, so now, of course, I want to give you an application of this, which I promised you the other day. So now that we've laboriously, and lest you fear that you're going to be doing such problems for days on end, you won't be. You might have to do one. But we will have a theorem that you'll prove tomorrow, which will save you from all that horror. So let's suppose let's say the point A, oh, I don't know, is like between 56, and the point B is 10.3. And my first question is going to be, what is the equation of the tangent plane? So you'll have some of these on web work coming up this week. Tangent plane to the graph at the point vector A. So the tangent plane, by definition, is the thing I was drawing in the picture the other day. You have a graph of a function, and we said you have the best linear approximation at the point A. You take the graph of the linear map, given by the derivative, and you slide it over so that it's going through the point on the graph. So this is the graph of the derivative map, and this is sliding that graph over so that it becomes the best linear fit at the point on the surface, just like we did for the tangent line to a graph. And we said the tangent line at that point is the line that goes through the point, but the linear function we're graphing is the parallel line back there from the origin. So this, remember, looked like y is f of a plus slope times x minus a. Well, this is going to be z equals height f of a, and then apply the linear map to the vector x minus a vector. That's going to be the best linear approximation to the graph at the point A at that. So this slides the map up, this slides it over, moving the origin over to the point A in the plane. And so you've ended up sliding the plane up. So what's the answer? Z equals, oh,
You haven't have yet?
well, actually, I didn't do what I wanted. So I got so carried away being smart, I did the wrong thing. So I gave you this is supposed to be my x, but I want to take an a that's near x where I actually compute f at a without much work. So I completely missed my own point. You're interested in computing f of x. X is going to be somewhere close to a. And you want to use the tangent plane at a to compute f of x.
Or you want the tangent plane at x to compute a.
No. So I want to pick an a where the numbers are convenient. What's a point that's close to this where f is easily computed? 350 and 10, right? Yeah, you could do either one. So the point is going to be, if I do the tangent plane at this point A, I can easily compute, the derivative matrix without too much trouble. And I can get the equation of this tangent plane. So what's f of a plus df of a times x minus a? Well, what's f of a? It's 350 over 10. Now the derivative at a, we said the derivative matrix is given by 1 over b. And then minus a over b squared. What's that going to be?
Minus 3.5.
Minus 350 over 10 squared, right?
3.5.
So 35 tenths, if you like, which we could simplify.
Sure.
7 halves.
Wait. Why are you adding?
He's doing the f of a plus.
So I'm computing this at the moment. So plugging in this a to that derivative matrix, I get 1 over b, and then I get negative a over b squared.
Then you're going to multiply
Then I'm going to multiply by x minus 350, y minus 10. So the equation of the tangent plane is going to be, in all its lovely glory, z equals 35 plus 1/10 of x minus 350 minus 7 halves times y minus 10. Now you can think of this as a formula like what you did in single variable calculus, where you use the equation of the tangent line to actually approximate the function nearby the point A. So this is like your delta x. You're changing x by that amount. This is how much you're changing y by. So in my actual case, with x being 356 and y being 10.3, we would have f of x is approximately, not exactly, but it's approximately the z I would get from the tangent plane. So I'm doing the linear approximation to estimate how much the function changed. And what would I get? 35 plus 1/10 of 6 minus 7/2 of 0.3.
3 times.
So this is 35 plus 0.6 minus 1.05. Is that what you guys got? 35 times 3 is 105. 3.5.
1/20 plus, so it's 34.65.
So I've got 34.55. So the punchline was going to be
Is that close to 356 over 10.3?
Sorry, I'm trying to focus on 2 things.
the punchline is going to be that this computation is taking how many miles Dan drove divided by how many gallons he just put in his gas tank. And although I don't really want to do long division of 356 by 10.3, this amount of arithmetic I can actually do in my head normally. So you can actually do, it's probably easier to stick to decimals and keep it rather than mixed in fraction form. It's probably easier to use decimals, 0.1 and 3.5, and then multiply and do this arithmetic. But this is the gas mileage. And you don't need a calculator, and you don't need a fancy cell phone that does calculators for you.
You just press the button on the display and it's like,
So
The next one's like,
all right, so what I'm going to do next, are there any questions on this? So the key thing is that you get to do the tangent plane to the graph of the function by basically saying that the tangent plane is the graph of the derivative. So you take the best linear approximation to the function. So you take the graph of the derivative, and that's what this term is, the derivative times vector, shifted so that it goes. Okay. So I'm going to end today by giving you an easy proof. Unfortunately, I don't have the definition of the derivative left anymore, but it's not no big deal. And we'll polish off these other results tomorrow. So here's a very basic theorem, f differentiable at A implies f continuous at A. So what does it mean to say f is continuous?
X approaching, vector x approaches
Okay.
f of x approaches f.
So I'm going to let x be a plus h, rather than letting it be x. I'm going to say a plus a nearby little h, add a little h to make a nearby point a plus h. And that's supposed to go to f of a. Which is the same as looking at the difference, and it should go to what?
0.
0. Okay. Well, this is actually not bad. We know that the limit of that minus f of a minus the linear map times h all over h goes to 0.
So can you break it up in this?
So if you're dividing the numerator by something small and it's going to 0, what must the numerator be going to? Right.
Yeah.
If you multiply this by magnitude h, law over magnitude h times magnitude h, right? The numerator is numerator over magnitude h times magnitude h. And what does the limit of the product tell you here? This is going to,
0.
and this is going to
1.
0.
Uh-oh.
That's certainly 0 still.
So we took that 1 over magnitude h out of the.
Yeah.
Right. I said if the numerator over the denominator is going to 0 and the denominator is going to 0, the numerator had to go to 0 even faster. That's what this says. Well, so the thing we're interested in, the change in the function, is equal to the limit of t of h. Linear map applied to vector, vector's going to 0, what does that go to?
0.
0, you did that in homework. You did that 2 different ways back in chapter 2, one with matrices, one without. This is 0 because linear maps are continuous. And you did this in homework in chapter 2, and I've forgotten the problem number, and I didn't bring my book.
7. 7.
7 in section
2.2.
That's this.
That seems
I don't remember, so I'm not going to write it down.
That was part of this problem set.
Yes.
Yeah, it's part of-
Yeah, it is.
It's the first problem on the problem set.
Yeah.
I just did.
Oh, which?
Okay, but so you proved for any matrix that the magnitude of matrix AH goes to 0 as H goes to 0. So this goes to 0, therefore this goes to 0. So since the linear approximation is going to 0, the difference in the function has to change, has to go to 0, which says it's continuous. Okay. So tomorrow we'll finish up the section and do a couple more proofs, and then we get back to more computational stuff for a couple days.